And today we are going to see about in fluid dynamics rate of change of linear momentum. The rate of change of linear momentum. Rate of change refers to d by dt. Linear momentum we denoted as m. So d by dm by dt. This only we have to find. So consider a fluid body whose occupies the interior of the closed surface S at time t. So consider the fluid body which occupies the interior of the closed surface S at time t. So m vector be the linear momentum at time. So time t, the m vector be the linear momentum with respect to the time t. At time t, the linear momentum may changes. So momentum can be expressed as in the terms of mass into velocity. Here mass can be, we know that mass can be written as density by volume. So density equal to mass by volume. So density equal to mass by volume, we need to know about the mass. So mass can be written as density into volume. Here density is denoted as rho and the volume is denoted as dt. So and the density is rho and the volume is dt. So this is defined as mass, and we know that the velocity is nothing but q vector. So our linear momentum can be expressed as q vector rho dt. Here rho dt refers to the mass and q vector refers to the velocity. By using the transport theorem, the rate of change of momentum, that is only mass into velocity, and mass can be expressed as density into volume into velocity. So for m equal to rho q vector rho dt, we get that. For a particular ds or dt, for particular space only we achieve our linear momentum. If we need to know about the whole circular body or whole closed surface, we need to do an integral. So m equal to integral of rho q vector d tau. Here we need to study about the rate of, we know that the momentum form is this one. We need to study about the linear momentum of the whole surface. So we do dm vector by dt and d by dt of integral of rho, which means q vector rho dt. So by using the transport theorem, we know that d by dt of integral of x d tau can be written as dou by dou t of x d tau minus integral of n vector dot q vector x into ds. Here the second term, this term refers to the flux of x out of s through the, which means the rate of flow of liquid outside the boundary through the surface S is denoted as this term. So dou by dou t of integral of rho d tau rho q vector d tau minus integral of rho q vector into n vector ds. This is known as the transport theorem. We simplify this form in the form of transport theorem. So then what we are doing means, by considering the second term gives the flux of the linear momentum s through the surface boundary, we can be we change this form into this notation. If we have integral of s a vector q n ds, means we can written as minus integral of, it can be changed into the surface to volume. So by using a Gauss theorem, we are changing this term. So a vector q n vector ds can be written as minus integral of v a vector for del dot q vector plus q dot del into a vector d tau. Okay. Dm vector by dt can be written as this term as it is. We are having this term, and if we take the integral outside, means, which means if we take the integral to this side, means we get this term, and this notation can be, this form can be changed as per the form of this, means we get, instead of a we have rho q, and here q as it is, n as it is, and ds as it is. So it can be changed into this term. So instead of a, we must replace rho q vector del dot q vector plus q dot del into rho q vector d tau, which means if we do the integration to both side, means we get the form of integral of dou by dou t of rho q vector d tau plus this term integral of q vector dot del rho q vector d tau and plus integral of rho q vector del dot q vector. Okay, we get three terms. By equating this term and this term from the material differentiation, we know that this can be written as d by dt of rho q vector. So this form is rho d by dt of rho q vector plus this term rho q vector del dot q vector d tau. So next what we do means we have this form d by dt, so we need to differentiate. So rho into dq vector by dt plus q vector into d, which means here dq by q vector d rho by dt. So we have in both term we have q as common. If we take q as common means we get d rho by dt plus, if we take q as common means rho del dot q vector into d tau. By the equation of continuity we know that rho d rho by dt plus rho del dot q vector can be written as 0, so this term goes to 0. So our rate of change of linear momentum can be written as dm vector by dt equal to integral of rho dq vector by dt vector d tau. This is the rate of change of linear momentum of the closed isophaseous at time t of the fluid body. Hope you all understand, and thank you.